So number 2, this one says a hoop. And by a hoop, what they're actually asking here is, or what they're specifying here with a hoop is basically one of these guys. So this is what I called in the class a ring, right? So we have a hoop that's rolling without slipping along a horizontal surface. Okay, so it looks like this. And all of the mass is concentrated on the outer rim. Something like this. Now it's a uniform hoop. What does that mean that it's uniform? The weight is distributed equally throughout, which means that the center of mass will be at the geometric center. So here's the center of mass. Notice that that center of mass is not even on the body itself. Does everybody see that? It need not be, right? So this is where the mg acts. Okay. Now it's rolling. So does everybody agree that we have rotational velocity around the center of mass? Does everybody agree that the entire body, think of this as the center of mass right here. Does everybody agree that the entire body is spinning about the center of mass? Does everybody agree? So we have this. But is it pure rotation? Or is it rotation plus straight line?
Rotation plus straight line.
It's rotation plus straight line because look, as it rolls, does everybody agree that the entire body spins around the center of mass, but also the center of mass moves in a straight line? So this would be pure straight line, what we technically call pure translation. This is what we call pure translation. This is what we call pure rotation. Now rolling means this, both of them put together. Does everybody see that? That is what rolling is. So not only is the entire body revolving around the center of mass, but the center of mass is also moving in a straight line, which we call VCM. So VCM is the velocity of the center of mass as the entire body revolves around the center of mass. So this is rolling motion. So here it is. We have a hoop that's rolling, and it says that it's moving forward with a speed of 5.5 meters per second. Which one did they tell you? Did they tell you this one or this one? If it says that it's moving forward, they told you the linear. Does everybody agree that the path that the center of mass takes is a straight line forward? Does everybody see? And what they just told you is how fast that center of mass is covering distance in a straight line. Okay. So that speed at the beginning is 5.5 meters per second. Okay, so now it says that it starts going up a ramp. Okay, and it tells you that the ramp makes an angle of 25 degrees with respect to the horizontal, okay, above the horizontal. So the question is, after it goes up the ramp a certain distance, which they tell you is 3 meters. So it's going to go up 3 meters up the ramp. Got a question. Is 3 meters necessarily the highest that it will go along that ramp?
No.
No. So it is not necessarily at rest after it has rolled up 3 meters. It can still keep going, right? So therefore, it's still rolling. So it's still spinning. So the body is still spinning about the center of mass. And the center of mass is still traveling in a straight line at an unknown speed, which I'm going to call VCM final. That should be less than VCM initial. Why should it be less than VCM initial? What happens to this body's potential energy as it goes up the hill?
It goes up.
It goes up. And as the potential energy goes up, what has to happen to the kinetic energy in order to keep the sum of the two energies, which is called total mechanical energy, constant?
It goes down.
It should go down. Does everybody agree that the kinetic energy should go down by the same amount? And by kinetic energy, I mean a total kinetic energy. So that's rotational kinetic energy and translational. Should go down in order to keep the sum of these two fixed, constant. Okay. All right, so we would expect that VCM final is lower than 5.5. That's what we expect, just from a physical analysis of this. All right, so now we're going to use conservation of energy. We don't have any dissipative forces here, so we can go directly for the conservation of energy without any non-conservative forces acting. So first off, I'm going to set my U equals 0. Remember, you can set your 0 for potential energy anywhere you want. Okay. So I'm going to set my U equals 0 line right here. This is where U is equal to 0. So what is the potential energy of this object right now when it is at the ground? 0. So I'm going to say this guy is 0 joules. Now, none of the other terms are 0. Because even when I roll up 3 meters up the ramp, I don't have 0 kinetic energy. Because I can still keep going, right? So none of the other terms are 0. So let's take a look. Let's talk about the initial kinetic energy. So does this object have kinetic energy when it is at the bottom? Does it have?
Yes.
Yes, it does. Why? Because it's in motion, right? So let's take a look. Kinetic energy initial. Now, do you agree with me, this is a statement I made in the lecture, that rolling motion is a combination of pure rotation and pure translation. By translation, I mean straight line motion. Does everybody agree? And if this object were just translating forward, in other words, moving forward in a straight line, does everybody agree that its kinetic energy would just be 1/2 mv squared? And if it were just pure rotation, its kinetic energy would be 1/2 inertia times omega squared. Does everybody remember? But if it's both, does everybody agree that I'm going to have both forms of kinetic energy? Because I have both forms of motion, right? So this is going to be K rotational plus K translational. Okay, so this is going to be K rotational, which is 1/2 the inertia of the body times the angular speed around the center of mass squared, plus, and then translational is 1/2 mass times VCM squared. So what are all these terms? So I is the moment of inertia, rotational inertia of the spinning body about its center of mass. Omega is the rotational speed of the body around the center of mass, about the center of mass. M is the mass of the body. Okay. And then VCM, that's the center of mass speed. So that is how quickly is the center of mass moving forward. That's the idea. Now these two are related. The rate at which this body spins is related to how fast its center of mass is moving. Because this body is not slipping. And if there's no slippage, you know that omega times r is equal to VCM. Which implies that omega is equal to VCM divided by r. Okay, this is the no slip condition. Remember, in this class, we won't deal with slipping. So what we can do now is we could actually substitute this omega right in there. So let's take a look at what would happen if we plug it in. So we're going to have K initial is equal to 1/2. The inertia, do we know what the inertia is for a hoop? mr squared. That one is actually given, and you don't have to memorize those because I will give you those. So it's mr squared, where m is the mass of the hoop. Same m that appears here, by the way. And then r is the radius of the hoop. So this would be, for example, from the center of mass to the outer rim. So that would be the inertia, mr squared. And then omega, using the no slip condition, would be VCM divided by r. And then don't forget that omega is squared. So we have this, but remember that we also have another part to the kinetic energy. Does everybody agree that there's also the translational kinetic energy part? So that's going to be plus 1/2 mass times VCM squared. Okay, does everybody see how we went from here to here? All we did was we allowed inertia to be mr squared because it was a hoop. That's dependent on the shape, right? So for a sphere, we did a sphere in class, it would be 2/5 mr squared. For a hoop, in this case, it's mr squared. If it was a disk, a uniform disk, it would be 1/2 mr squared. So this is shape dependent. And then this is always true as long as there's no slipping involved. So that would be VCM over r for omega, and then the whole thing is squared. Now, you got to remember from math that if I square a fraction like this, it's the same as squaring the numerator and the denominator simultaneously. So I have VCM squared over radius squared. And the first thing that you'll notice here is that what happens to the r squareds?
Cancel.
They cancel. Very good. So the r squareds are going to cancel. And you're left with kinetic energy initial is 1/2 mass times VCM squared plus 1/2 mass times VCM squared. And I should be very specific here. This is the VCM initial, since it's initial kinetic energy. So I should be very specific. And that is a quantity that is known, that is given to you, right? And if you notice, both of those terms are identical. Does everybody agree that they're identical? It's not always going to be the case, because this here depends on the shape. Does everybody agree that the inertia depends on the shape, and therefore the rotational kinetic energy in terms of the center of mass velocity is going to be shape dependent? So you're not always going to get the same exact expression. So that's something that you need to be able to handle for any shape. So kinetic energy initial would be 2 times one of these, 1/2 mvcm initial squared. Does everybody agree that I have 2 of them? So take one of them and double it, and that's our result, right? So what happens to the 2's? They cancel. Excellent. So that means that the total kinetic energy that this body has, it's mvcm squared. Exactly. Now again, that is not something you just want to blindly remember because it is shape dependent. So this is something that you have to be able to handle for any shape. So if I have you do one with a sphere, your initial kinetic energy is going to be completely different. Okay. So, all right. So now here's the good news, though. Once you do it once, you don't have to do it again for kinetic energy final. Why? Let me explain why. Do you agree with me that since at the top here, after it's rolled up 3 meters, it's still going to be rolling? Does everybody agree? It's still going to have rotational kinetic energy, therefore, and it's still going to have translational kinetic energy, therefore. Would you agree with me that I would still have this? And if I still have this, the inertia hasn't changed. The inertia of a hoop is still mr squared. The mass hasn't changed. The radius hasn't changed. Does everybody agree? So inertia hasn't changed. Omega is still V over R. But this time V final, that's the only thing that changes there, right? So you would have VCM final squared over R squared. Plus 1/2 mass. Mass hasn't changed.
Or am I interrupting?
Yes. Yeah, we have a review session. So we're going to be done probably at around 1:30.
Okay.
Yeah. Thank you. All right. So this guy's the mass. This guy here doesn't change, right? It didn't change when it rolled up the hill. What about VCM? It changed, but it has the same form, right? But it's final this time. Does everybody see that? So everything stays the same except VCM is actually now final instead of initial. So the good news is that once you've actually calculated kinetic energy initial, kinetic energy final is going to be exactly the same expression, but using the final center of mass velocity. Does everybody see that? Okay, so now I've got the 2 expressions, and now I really only need one more thing. I need the final potential energy. Why? Because take a look. I'm using conservation of energy, remember. So U initial was 0. I need these 3 ingredients, and then the problem is basically solved. So I have kinetic energy initial, I have kinetic energy final. Does everybody agree with those statements? The only thing that is missing is I need to know how much of this initial kinetic energy was transformed into potential energy when that object has rolled up 3 meters. Now, what was the equation for gravitational potential energy? Mass times gravity times height. Very good. So does everybody agree that this object has rolled up to an altitude? Is the altitude 3 meters?
No.
It is not. Does everybody agree that I would need to use some trig in order to calculate what this altitude relative to the U equals 0 line is, or relative to the ground? So that h would be, it's a projection of this 3 perpendicular to the ground, which is opposite basically to this 25-degree angle, so that would be 3 times the sine of 25 degrees. Okay, does everybody see how we got that as the altitude? So that's going to be 3 times the sine of 25, so I have 1.27 meters. That would be the altitude. Does everybody see how we got that altitude? Okay. So now the potential energy final, I'm going to go ahead and write it over here. Potential energy final would just be mgh, but in place of h, I now know that h is actually 1.27 meters after I've rolled up 3 meters up the hill. So that's going to be mg times 1.27. Okay, so everybody see how we got that? Okay, so now I'm going to plug everything in to the conservation of energy equation. So I have U initial plus K initial is equal to U final plus K final. Remember though that What was my U initial when I was on the ground? 0. So now I'm going to substitute all of these guys in. Kinetic energy initial is mvcm initial squared. Potential final is mg times 1.27 plus kinetic final is mvcm final squared. Now you notice that every single one of those terms has an m in it, right? Does everybody see that? So I can divide through, since m is a non-zero quantity, I'm allowed to divide by it, right? So I can divide both sides by m. What that means is that m over m is 1, since m is not equal to 0. Here, m over m is 1, and same thing here, m over m is 1. So that m actually cancels out, since it's a non-zero quantity. So I'm left with VCM initial squared is equal to g times 1.27 plus VCM final squared. Does everybody agree with this statement here? Does everybody see that? So now, take a look. Do we know what the initial center of mass velocity is?
Yes.
We do. And we know what g is. 1.27 is just a constant. And therefore, that allows us to now calculate VCM final. Does everybody agree? So let's take a look. So I'm going to go ahead and plug in VCM initial, which was actually given, 5.5 meters per second. So 5.5 squared is equal to g, which is 9.8, times 1.27, plus VCM final squared. So now I'm going to go ahead and rearrange this. So VCM final squared is equal to 5.5 squared minus 9.8 times 1.27. And then the last step is you take the square root. So let's see what we get. And we expect it to be a number less than 5.5, which you can already see that it will be.
About 4.2.
4.2? Okay, so let's double check. So 4.2, yeah. And what are the units? Meters per second. Excellent. So this would be VCM final. Now, question. What if I wanted the rotational velocity of the body about the center of mass in its final configuration? In other words, I'm looking for omega now instead of VCM. What would I do for omega? Would I have to do all of this over again, or is there an easier way? Very good. So omega final would be VCM final divided by the radius of the ring, right? So VCM final is 4.2, and then the radius of the ring, they actually told me. What was the radius again? Did they tell us or no? Okay, they didn't tell us. Well, if they did tell us, we would be able to calculate what omega is. Since we don't know what the radius is, we actually cannot calculate omega. We can calculate VCM, but we cannot calculate omega. All right, so I'll just leave it in terms of R then. So if we knew the radius, we could actually calculate it. All right, so is everybody comfortable with this one? Is everybody good? Can I clarify any of the steps? Is everybody good?